for the whole points. Okay, but let's discuss. So it's like some approach. It has good properties, as we see, but let's discuss its problems because we need some motivation to analyze boosting. We can introduce boosting as an attempt to solve this problem. So the first one is a consequence of that we could reduce variance but not introduce additional bias by backdating models. And it means that if this guy, any of base models, is biased, so the sign has the same bias. And this does mean that we could learn more and more these algorithms. But if bias is great, it will not help us. So it's not will reducing, and we will make systematically mistakes. Other issue is that we are learning usually like big amount of large number of modules. So in one way it is okay because we learn them independently. So in time complexity is okay, we could do it in parallel. On the other hand, we learn them like independently again. And so they don't share any information. And because of this, we need very large n to reduce our variance sufficiently. And so it's like large n, it's some costs to store this, costs still to apply, because one time we could do it in parallel, but still we need some like much computational resources maybe. And also like consequence of large n, it's a lack of interpretation. Because we usually ensembling trees. Yeah, and why we love trees, because in some way we could, for example, plot the whole structure of tree and make some interpretation. When you have like 5 trees, it's okay. You can still plot each tree, see rules, and make some interpretation of what is important. But when we have ensembles like about 500 trees, it's not usually possible. So if we could somehow to reduce this number of elements in ensemble, or another way, if you could reduce the depth of trees in ensemble, it will be good for interpretation, and also could solve these possible issues of storing and costs of applying. Okay, so let's introduce boosting, like something very opposite to backdating. Let me make this column for boost and this for backdating. So here we will take very simple models. And when I'm saying simple, it's like more, so it's not linear regression. By simple, I mean something that has like a big bias, but low variance. As an example, you can keep in mind something like a decision tree with only one node. So it's like called decision stand. In contrast, in backend, we use very, say, complex. It's not very rigorous, but it's okay. Very complex terms that it has very big variance and small bias. And as example, you can imagine that, of course, it's very depth trees with very big depths. And so it's also sensible that because if backend saves the bias of each member of ensemble, so each member should be has very small bias, it costs for us big variance, but when we aggregate, variance reduce. In boosting, like very opposite approach. We would like with each member of ensemble reduce our bias of the whole algorithm, but then we need to each model be low variance. And this is like different, we attack the same trade-off with different size. Okay. So as next, we will build our models sequentially in boosting. And as you remember, in bagging, they're independent. So we build them there in parallel. And this consequence of, so why sequentially, is that we would like, we cannot read it. Like say it's each new model correct previous. And this is very drastic again with the bagging, because in bagging, each new model knew nothing about other models. And in boosting, it's not very correct. We would like to reduce number of models. We would like that each new model will influence to whole our ensemble in efficient way. So to do this, each new model will look on the outputs of each previous models. Okay, so here is like our plan. Let's make it more formal. And let's develop the theory of how we will implement this plan, how we will learn like in practice way, what's the procedure of learning. So again, this whole sum is our ensemble. These guys are base algorithms. And we would like to use prediction of this whole guy. So the first process is how to learn the first model. And we say, okay, we knew how to do this. For any task, we introduce the loss function. And so we have the train that's set. So we just calculate the loss in each point, average them over the whole data set, and minimize over the parameters of the first algorithm with gradient descent, if it is like differentiable model, or with greedy search as for example, tree. Okay, the first model is very clear. Okay, then What about vectors? So we would like to learn and model while we have all this model fixed. So this guy is the sum fixed already. We learned it in previous steps. And this guy we would like to learn. Okay, and you can see that it's a bit tricky now because we didn't discuss, for example, how we can do this, how to solve these problems. For example, for linear regression, maybe it's okay. We just can take the gradient about parameters of this new loss and it's fine. You can do this, but it's like not very much sense of learning to learn boosting of linear models. Yeah, and usually what we do, we learn to boost trees. And so this problem is very modified for tree. So somehow we need to modify our loss, our training procedure. Okay, let me. So again, we learn and model. So and we have a couple of questions. So basic problem is that we don't know how to optimize this functional over only BN. Yeah. And like to have some freedom that we not, of course, in a particular model, we could somehow converge to idea how, okay, for this particular model, we could solve this task. But the general property of making ensembles that we would like to have is that it should be like model agnostic in some way, that we could make boosting or bagging for any model. And each model has its natural some procedure to learn, to optimize its own. And we would like not to very much modify, keeping the same, but maybe modify the targets or modify some scales. So we need to introduce modifications. But suitable for any model. Okay, and before we introduce them, let's make some outlines. So what we need to recap from here, that we learn sequentially. New model is, let's say, condition on old models. And at least try to correct them. And we need some new training routine. And like, let me also know that it's opposite to bagging idea. Yeah, because it will like somehow easy to you to find for each algorithm place in your head by saying, okay, it's bagging and boosting, it's opposite one. What is true for bagging always wrong for boosting. Okay, like let's consider the first and so maybe most easiest and intuitive example. It's a boosting for like mean squared error. So it's messy, and that means that you solve regression task. Yeah. And like, let me recap. Okay, maybe here. Again, we have like this ensemble. We need somehow to use this guy, train it. And for now, we say, okay, it's too abstract to solve. Let's consider this guy to be a messiah. And then we'll see how we could modify it. Okay, so this guy is our messiah loss. And you can see why it's like the most easiest loss, as I could say this, because for now we have that this red guy, the prediction of our model is just an additive mixture. So we predict from this guy, then we predict that which already fixed from this guy, which is we train, and we just sum up. And then to estimate the error, we just make our like some observed point minus prediction. Yeah, and then we could just rewrite it a bit. So it's our output, this guy we observe, and thanks to distributive property, we could just like make this one. Or better, okay, it should be here. Okay, we just modify it. So you can see that it's equal to this. We just open brackets and a bit distributed. Okay, so let's call this guy as SI, and SI let's call like it's a residuals. Okay, and in this case it's like very natural idea because so in some sense the new algorithm is learning to fit to the residuals or errors of the each previous algorithm. And it's exactly that much our idea. So let's call that this is then matching residual. And this is very aligned to with our idea to reduce errors sequentially. So here, for each object I, we look on the error at this particular object I in our training set, and new algorithm trying to reduce these errors for each object. So and here, if we have like no error in some object I, we perfectly fit it. We have here 0. So the new algorithm should add nothing to our composition. And this is like very useful property, of course, because we should control not only reducing old errors, but also not making the new one. And if for some object we don't have errors, let's not introduce them. So this guy should be 0, like the whole bracket. saying 0 if already no error. Okay, what is important, what is like, I would like to emphasize it when we learning, it's quite obvious, but still, when we learn a new algorithm, it should not only reduce errors on the where we have them, but also not introduce new one if we already don't have them. Okay, okay, let's consider like some very stupid example just to keep our intuition. So for some object we have an output 12, and we already have an algorithm of like n-1 models that output 10. So then what will be residual? Of course, it will be like 2. Okay, so then like this guy should be learn plus 2, and this guy then should output 12. Okay, very basic. Okay, so now we know how to do boosting because we know first iteration how to do. It just feeds this model. Okay. Then like we have second iteration, and we also know what to do. We say, okay, we need to, for each object, we make some new label. Yeah, and then like second model is learning on these new labels. And what is important is that we don't know who is B, what is the algorithm. We don't care. So this modification works for any algorithm. And this is quite desirable result because, again, maybe new algorithm will be developed, or we would like to use different B, and then like we would like to keep this our procedure of making ensembles. So when here we get it because of the properties of MSE laws that we could break laws, could a bit like apply a distribution law. So we could put brackets whatever we want, and we put it here and say, okay, it's our new answer. Learn each new algorithm to it. Okay, let's see how it will work. For example, what it will be fit. So we have like one-dimensional problem of regression with this. So it's our answers. This is only our feature. This is our data points. Let's feed them. Okay, let me zoom. So, and we feed here, as you can see from the image of the decision plot. So a tree with depth 1. So it's saying, okay, that from here, sorry, like separate into planes, and here it will be mean answer this, and for points in this, mean answer is this. So we have this model. Okay, then for each point, we could find this difference and like plot it here. Okay, and this is our residuals, and you can see that this is really like new data points, because then again for each x, which is the same in our original training data set, you have some new point with some different target value. Okay, so that we can then make iteration 2, and it's all the same. So we see that we have, where we have errors, we have bump here, then we have perfect fit here, and like estimate new residuals. And one more time. So we have some. So what is important here is that you see that here we have no errors, but here we have some like error, and at new iteration we had kind of trade-off, so that we a bit increased error here, but we much decreased error here. Okay, and then like algorithm consistent. Why it's so? Why we didn't like learn something that in one step reduce both error here or keep here, for example, keep here no errors and reduce this. This is because that we talked about that for boosting we use basic algorithms which has low variance. Like in some sense big bias. Yeah. As example, it was like decision tree with depth 1. And this limitation limit like expression of our algorithm on each new step. And so it not reduce all errors to 0. It will reduce some errors, but introduce a bit new one, and this help like not to our algorithm not to overfit completely. Okay. Okay, so we can fit, and finally we'll solve this one-dimensional problem. What is more interesting? Let's say, see how it works. How we could observe this bias variance trade-off for different algorithms. So this guy is like random forest, so it's more or less instance of beginning approach. Okay, so what we see here, that as more estimators we're taking in our ensemble, the error starting to reduce, and then it's like more or less with some small aberrations due additional randomness of random forest, which we also select different features, but still it's starting to saturate and keeping on the same level. We see that's like it's stable plateau. Number of estimator is growing, but error is not growing, and also it's not dropping. And this is typical for begging. Why? Because so what we did? You remember that like error is somehow bias plus variance plus noise. And if we have for each algorithm same bias, begging keeps these terms and decreases. But it decreases when? Not all the time that we add new algorithm. And decreases while like the covariance between, let's say, previous ensemble and new element and big is 0, like approximately 0. And when we like learn sufficient amount of the trees, of elements of our ensemble, like the 161 element of ensemble, it's be very likely something that was before. It will have very much covariance. So this guy is not equal to 0, and this term is not dropping more. It's like constant, and all other terms, PS and noise, it's also constant. So from some number of, so there exists a number of estimators that saturate our diffusion of error. Let's see now for boosting. And you see that it's a bit like completely different story. So what we have here, again, this is loss, this is number of estimators in our ensemble. Okay. So, and you can see that we taking them bigger and bigger, we could what do? We could decrease our train error to 0. And if I'm like, I could make like this kind of plot. Yeah, this sends 100 numbers. But for the test set, it will starting to increase. It will increase very slowly. Yeah, but still it's starting to increase. And so this is why, because okay, it's not why, like it's two questions. Why slow increase of overfitting? Yeah, it's because we use some simple models with very big bias and low variance. So if new model is very simple, it cannot overfit drastically. So, but somehow still, of course, if we add and add, so this bias will starting to reduce and we will starting to overfit to training dataset. But starts from sufficiently many estimators and still the whole procedure is effective. Of course, when I've saying sufficiently big, it depends on what you use as your base estimator. Because for tree with depth 1, it will be like 1000. But for trees with depth 3, it will be 100. And depth 10, it will be 50. Okay, so keep a bit. So it's common to say in statistics words that boosting is some procedure that is not overfitting and like very robust overfitting. But in practice, like you don't use some decision stems or trees with depth 1. You use something which is like has a bit more variance but a bit low bias. So it's something that should be checked as always with cross validation and so on. Just be accurate with it. Okay. Okay, so let's make some outlines here. What we need to like to save in our memory is this whole story. So it's just 2 points. So first one, for MSE loss, it's fine. We know what we do. We just define new labels. Yeah, and we can then train any algorithm on them. And it's like first point and second point that boosting can overfit. So all usual considerations of cross-validation for like hyperparameters, so on. Okay, you should use it, which is again a constant in contrast for bagging. For bagging, if you have like computational resources, you can just put 1000 estimators, feed them, and apply if you would like. It will be okay. For boosting, you cannot do this. If you feed, you can drastically overfit with them. Okay, so then we find this MSE, but what about other loss functions? What about like classification problems, or maybe like so. We can break it into parts. First, of course, we somehow need to introduce recipe for classification. Yeah, because we don't want to solve only regression problems. But then also, if you would like to maybe to solve regression problems, somehow MSE is very symmetric. Yeah. But for some problems, we could say, okay, it's like we would like to use like this type of loss, which is let's call it quantile loss. Yeah, whereas this like non-symmetric penalties for each line. And so somehow we should modify our procedure or see will it work. So again, we have such problem to optimize. So we need to learn and model. So this guy is already fixed. And so this guy we need to optimize. Okay. So okay. So what kind of idea we could explore? Again, we said, okay, this is something just some general laws. And then we could say, okay, for MSE, it worked. Will it work for some other? Yeah, then we just to apply directly this idea, we say, okay, we don't know how to solve this. But we know how to solve this. So we could fit our new estimator to this difference, as we did in MSE. But it's like, as we will see, it's quite a problems, mostly because of the space of support of our targets. Yeah, because when we like solve a regression problem, our targets like in like just real line, which is very beautiful space. Add numbers, subtract numbers, any number has its sense. But for example, if we have a classification problem, it's starting to be tricky. So here, for example, it's okay, but here what is sum of y? It's not clear what is it, and then it come problems here. Okay. Let's see like a particular example. Yeah, here it is. So we use like logistic regression. Yeah, so here is our loss. This is like our classification rule. And let's modify it. Our targets as the following: we take the difference. So it's called what we call residual, and then multiply by new algorithm. Let's see who is who here. So this guy is output something like plus minus 1, because this is how we defined our classification rule. For each n, the whole ensemble is output the sign of the sum of base learners. So this guy output plus minus 1. Okay. This is our labels in the training data set. So it's also plus minus 1. So let's see what possibilities then we have here. Yeah. So if this guy was plus 1, and this guy could be also plus 1. So we have here 0, minus 1, also 0. And like if they are different, we have plus minus 2. Okay, what is same class? Two things. So with this, we like saying, let's say, okay, somehow we have an error on a data point. We have like some weight to learn on it. Of course, it's a kind could be discussionable. Is it a good way to fit to plus minus 2? But at least it's some signal, some number that indicate to our algorithm that okay, fit here. Here was an error. But here we have a 0, and the problem here with like a bit difference with the loss. That here you can see that we have between these two brackets, we have multiplication. So when for object E we awk, then it will be 0 multiplied on our new algorithm that we learn. And so it will be whole equal to 0, and we just will not count on this point. It will be dropped from the sum. And the sum will contain only these points that we have not made an error. And like you can see that is not the desirable property of what we would like to learn, because just we will fit to the points in which we have errors, but we will forget all information about points which we already know. So when we starting to associate between them. Okay. So let me here write it one more time. So if we have that our current ensemble is output correct answer to the data point I, this is like we don't count, we don't use this object for learning this guy. And as consequence, so this model could output anything. For an object I, and it will break the whole condition. So the conclusion, like it was not general way. Introducing this kind of residuals to the general loss, which is different from MMC, it's something wrong. We cannot do this. We need to develop some like further theory, further methods of learning boosting. Okay, let's skip this because it's like the same. So we could try on some way to fix it. We could, because okay, we have something with what we have the problem here that it will be 0 if like and then we could take the logarithms to this be additive and like to say that mimic MSE loss. Of course, it could be done, and so we could introduce this guy, yeah, but still it's like the general way. So if I modify the loss one more time, it will be different, and we will need to introduce some other tricky way. So because then you can like somehow for your observable worldwide observation, okay, it exists, but like it's no need to remember this. Okay. Okay, but let's like develop our intuition about complex functions. Yeah, and this is very similar which is what we used when we discussed the gradient descent. Because of course we have some our loss, maybe like something it's smooth, but so it has two optimas, like and so on. But we know that how to work with MSE. Yeah. And MSE is just was some quadratic function. And basically, what was the intuition of gradient descent? When we, for example, would like to minimize some function over x, we say, okay, we don't know how to minimize the whole function. No idea how to do this. But we know that if for current, for example, if we stay at this point, we could say, okay, our function is something like this. And this leads for us to the gradient descent update rule. So then we could minimize this over x, this guy, and it's saying for us that mu x here, x0 minus gradient in this point. Okay, and if we here introduce some like alpha, it will be also like a step here. What's the idea of this whole story? Is that we have something complex function in gradient descent, but then we say, okay, let's use like this kind of model for it. Yeah, what is this kind of model? Over x, it's like here this function is linear because it's constant, it's a linear, and this kind of quadratic. And for this function, we could solve it and say, okay, update x, new x is this one guy. What's the story for our boosting? We know how to solve it for MSE loss, which is what? Which is quadratic. So you see here we can solve the problem for the quadratic loss and develop update rule. And here for quadratic loss, we could develop our updation. Yeah, but like also similarity which shares these two approaches that we would like solve the problems not for quadratic functions. And then in the gradient descent, we say, okay, we could somehow approximate our function with quadratic in this particular point, x0. So we need to do in boosting, but our point is the algorithm. Okay. So again, we would like to explore Ants model, and let's like use our intuition developed from gradient descent. So this guy is our current algorithm. What does it mean? Like it's our current point. Yeah. So these points, this whole loss could be approximated. That okay, we stay in here. Plus what? Plus the derivative of loss. In where? In our current point. Multiplied by like difference. And here we could add like the same quadratic root. And so we will derive the gradient update for this guy. And so what is like in terms of residuals and so on, we could say, okay, we define this guy to be residual. It will be just like the negative gradient of loss in which point? In the point of our current algorithm, which what we already could output from our ensemble. So we just will modify our loss in that way, and that's all. So here we take derivative. Okay. This is what we observe from our data set. This is our, and this current ensemble, let's say, output. Okay, so it's very like gradient descent, but it's gradient descent over the points of our ensemble answers. Yeah, and let me emphasize not parameters. Because here you can see that like we don't talk or speak, we don't speak about parameterization. Of B. We only care about like output space. So whatever B is, I am only curious about if I put on it some object xi, what output will it produce? And only these outputs will influence on my residual. So I would like to learn to match. No any kind of parameters involved in learning. Okay, so this guy could be like positive or negative or equal to 0, and in somehow like direction of changing, which is again important that it could be equal to 0 or like be small, that in some object which we already not introduce some errors, we will not change. So this guys not change when no mistake. And this like somehow to how to change in so it's if it's regression, it's easy. So it's like really shifting vectors of our prediction. If it's for example sophisticated, for example, like for 3 classes we have simplex, and we could say that we some in space of logits, but like for intuition it's just to getting flow, like modifying decision boundary, it's to be margin less or bigger on other objects. Okay. So we just send these guys our new residuals. And then for each algorithm BM, we would like to fit it to minimize the distance between these residuals, between the direction of the derivative and new algorithm. This is our new model. So our base model on X side should output this guy. So and fit our base. And so because you what is important, this guy is lying again in the real space. And so we solve some simple problem of projection. Yeah, we minimize again something like MSE loss. And for this loss and simple loss, we have a lot of different routines for any algorithm how to solve. Any algorithm is you can imagine we could it's starting like its construction is starting to solving the problem for MSE loss. So it could be tree, it could be some, let's say, neural network, whatever. So gradients methods or just greedy construction methods. It's okay, we can do this. Okay. So again, we fit ends model. These guys are our residuals. So let's say that it's a gradient descent in answer space. It's the first point. Okay, second point that by taking the derivative of the loss, like we use local information. About loss function. Remember that usually, like when we discuss GLM models, yeah, we introduce like different losses for classification, for regression, for Poisson regression. But what was like similar, it all was convex losses. And all convex functions somehow look like let's put it's better, right? Like quadratic. So what I would like to say is that all convex function quadratic function. So then all convex loss is locally MSE loss. Yeah. And by introducing, like by taking the derivatives, what we really do is we're trying to locally solve this problem of boosting with MSE loss, which is very natural to solve. We, like in the start of the lecture, we developed this approach very easily. Okay, let's see some particular examples. So this guy is MSE. We take the derivative of this, and we have like this difference, which is you can imagine like we developed by just intuition in the first slides. And so it's to check every general approach on some very simple case that they match. That's okay. At least we don't break MSE. This approach is fine. Okay, and it was like the same update. Okay, we then consider like this one for regression. Of course, as human being, I draw a symmetric case. Okay, let's do the same. It looks like this guy. Okay, and so like we have here indicators, but it's like we just straight through to take the derivative, and so this is our derivative. And you see that in different points we will use different kind of multipliers here, and we count like in a symmetry in our loss function, because here you see that we have like square here and like the difference here, and here we have like the same, but this guy is multiplied by 5. But does it like multiply everywhere? Not, only locally. So for every yi with some concrete I, we know what to use, this one or this one. So locally it's again like a scheme. Okay, let's skip it. Okay, and same stuff for logistic. We just take our loss function, take the derivative, and here we could like analyze it and develop more intuition on it. Let's go here. Okay, so this is our derivative of loss, and so we then to fit solve this problem, we project a new algorithm to these residual guys. So, and for this algorithm, okay, this guy is the margin. So if it's much more greater than 0, this guy is much greater than 0, and so this whole is like equal to 0. Yeah, and is this end for us okay? Because when this situation is come, when we have big positive margin, when we have some point which is like which has like big distance between it and decision boundary. On the other side, if this guy like big by modulus absolute value, but it's very less than 0, then we have plus or minus 1 here, and we know how to modify it. So we learn on these errors. Okay. Okay, just a second, try boost. Okay, so let me have like empty slides. Markets like we discussed how to fit the boosting projection. We will next discuss some hyperparameters and how boosting is sensitive to it. But before this, let's like have some time for your questions, because I'm told a lot of information. Maybe For some of you very new, for some of you maybe not very new, but please ask me some questions or share some your thoughts about your experience with boosting, or so whatever you want. Okay, let me ask you then. Okay, Dmitry, do you know about boosting before this lecture? Okay. Okay, so then let's, I will just, okay, let's then discuss more. I will ask your opinions about hyperparameters. Okay, so very first natural hyperparameter is like the step size, as we have in gradient descent. We have some step size, and here we also have like step size. So then we could call it learning rate, but it's like in some, like, I believe in XGBoost it has this name as it's the library. Has this name as hyperparameter. But just be patient with, like, firstly we cannot limit with one here, but usually we don't use much more. Why? Because it's easy to see that what if we take it near the zero or exactly zero, we modify our algorithm in very small way. Yeah, nearly not modify. When we take it something very big, we can modify our answers very drastically. And so, wait. What we can conclude from here. So less learning step, then we need more ensemble members. Second thought is, let's remember that it was a recommendation to use some with each algorithm has big bias, but low variance. And then it's like very simple thought that if each van has big bias, so it's not maybe a very good idea to use a very big step size. Yeah, we all do locally. We also approximate our loss very locally. So if you do something locally, then do this very small step size. So we can sort the step size as like some trust region around our current models. Yeah, when we know how to modify. Okay. Again, in practice, it's not clear what to do, because big bias, it's again is depend on the data set, on the models that we use, on the depth of the basic trees that we boost. What is big bias, what is small, so you just put some fixed other parameters, and just make some cross validation here, and that's it. So, but you should have some intuition that bigger step size, it's introduce bigger bias with each new algorithm. So it could affect in not very good way. Okay, so we can see here a plot with different learning rates. I hope you see something here. Okay, so let's see who is first starting to grow. So this orange line has like learning rate 1. Yeah, and it is the most biggest in this picture. So then next, this guy, blue guy, is learning rate some round 1, and this blue guy is something this big. So this is a bunch of big learning rates, let's say that. And it's very fast starting to decrease the error. So it's like, let's say, something like this. Yeah. But then it's error starting to grow. Yeah. Quite the opposite if we take the very small learning rate. So this pink line is very small. It's like not reach the level of the error, which is reach, for example, yellow line, which is starting to grow. And same story for all its friends. So this guy has like this learning rate, and like of course it's reach a much less error, but in 1,000 trees, because like less step size you making, more trees you need. And like this is again some trade-off. So here's a number of trees, here's the error. So here you can reduce the error like in the same level with 150 trees, and here is 1000. So you just need to, as which is always trade-off, you need to use cross-validation. Okay. Okay, as always, when we're talking about regularization, the like biggest friend of regularization is randomization. It's like general thought in machine learning. If you could randomize something, randomize it, it will act as regularization. And like if we boost usually trees, you know what to randomize here. It's a feature space, sample space. So on what object you learn, what features do you use? Okay, and like here you can use more, and here maybe you can use more aggressive randomization than in random forest. Yeah, because like if you like, for example, we can use only 10 features from thousands of features for each tree, and will be not very good for bagging. Because why? Because in bagging we care that we have low bias. So we're saying that usual practice is taking the square root of number of features, so logarithms, whatever. So it's quite big. Because we need to maintain low bias. Here we will reduce bias for each new step, and then because of this, we can reduce the number of features in drastic way, and this is like will decrease the variance and taking care of overfitting. Same stuff with sample size and so on. Okay, so I believe I used my time. I hope you have some intuition about boosting and how the whole algorithm could be developed from scratch. So if you have some questions, please ask. If you're not, so bye. Have a good day.